When looking at commercially available op-amps, one question quickly comes to mind. Why this mind-boggling variety of commercially available op-amps? DigiKey, an online electronics component store, lists more than 34,000 different op-amps for sale. These op-amps all have different characteristics that make them more suitable for certain applications than other. Good design is about selecting the right component. And to make the right selection from this vast selection of available op-amps, a solid understanding of op-amp characteristics is required. The key element of practical amplifier design requires choosing a device whose characteristics fall within the design requirements. The signal degradation caused by the op-amp appears in the form of distortion, clipping, saturation, DC offset, noise, attenuation and phase, time, shift. In the next sections we are going to investigate op-amp characteristics and their influence on performance. We already explored frequency-dependent signal attenuation, or finite bandwidth, using either the single or double pole op-amp models. We start our analysis of the op-amp characteristics that leads to signal degradation, with output signal clipping or saturation. What happens when the output signal gets too large? Let's use an example, where the input signal to the op-amp is 1 mV, and the open loop gain of the op-amp is 100,000, or 100 dB. As op-amps go, this is quite a large open loop gain. The voltage at the output of the op-amp should therefore be 100 volts. This of course never happens, because the output of the op-amp cannot rise above the supply rails. Let's use the ideal op-amp model to investigate what happens under these conditions. In this plot the input voltage has a peak of 1 mV. And in this plot, the output voltage is shown with a peak of 100 volt. As we already said earlier, this is not possible for a real op-amp to produce a 100 volt output. The output of a real op-amp saturates or clips at the rail voltage. This means that the output voltage of an op-amp cannot be more than the supply voltage. So, how do we model output saturation or clipping? This is the subject of the next slide. This schematic shows the ideal op-amp used in the previous slide. This is what the ideal op-amp circuit looks like, with the addition of a positive rail clamp circuit. The positive rail clamp circuit consists of V2 and D1. And this is what the output voltage looks like, with a positive rail clamp. The output voltage is clamped at about 5 volts. The reason that the output voltage is not clamped at exactly 5 volts is due to the forward voltage drop across the clamping diode D1. This voltage is set to a very low value in the model used for D1. In this example, the forward voltage drop of the diode model is set to 1 mV. This is what our basic or ideal op-amp model looks like, with clipping added to both rails. This is what the ideal op-amp circuit looks like, with the addition of a positive rail clamp circuit. The positive rail clamp circuit consists of V2 and D1. And this is what the output voltage looks like, with a positive rail clamp. The output voltage is clamped at about 5 volts. The reason that the output voltage is not clamped at exactly 5 volts is due to the forward voltage drop across the clamping diode D1. This voltage is set to a very low value in the model used for D1. In this example, the forward voltage drop of the diode model is set to 1 mV. Let's explore another example of output clipping, with a lower input voltage. The input signal is reduced to 60 microvolts, and the open loop gain remains at 100,000, or 100 dB. The output voltage without clipping will be 6 volts. And this is what the output signal looks like. The output is clipped at plus and minus 5 volts. But because the peak amplitude is lower than the previous example of 100 volts, 6 volts in this example, the clipping is less than in the previous slide. These are the circuit models for the ideal op-amp with output clipping. It is set up to calculate the transient time domain response for the first 500 microseconds. In this assignment, we continue the use of the dot step command to vary a specific circuit component or parameter over a range of values. In this example, we use the dot step command to vary the input signal amplitude from 2 microvolts to 10 microvolts. Use this LT-spice file to investigate the behavior of the clipping circuit for different input signal amplitudes and open loop gain values. The value of the clamping voltages must also be varied. Also use the simulation with different input waveshapes. This brings us to the end of this section. In the next section we are exploring the slew rate of an op-amp.